you. So it's a pleasure for me to introduce you George Todd, who has quite an interdisciplinary profile. So I'm skimming through his CV. He had a PhD in mechanical engineering. Then he made the first postdoc at ULB, more on robotics. Then he moves to the Flanders Make Research Institute. He was back to ULB as a student in data science. And now his future will be in Paris as soon as he will be able to move there to start a postdoc on physics-inspired machine learning. So he contacted me in order to know a little bit what was happening in the machine learning group. So he was wondering if it was possible to take part to the research life in MLG, but there is not much life, social life taking place in this moment. So I prefer to invite him making a presentation. So I think it's a good occasion to know each other and to know your research. So don't hesitate also to tell us what are you supposed to do in the future. And then thanks for accepting our invitation.
Well, thank you very much. It's very nice as well on your side to accept me. Yeah, on the very long term, I would like to stay in Brussels, but so we will see how things go. Yeah, let me start. Okay, so I'm going to talk about how to discover natural laws from data. I hope you're not going to be too disappointed by the title because it's very ambitious, and what you will see is a little bit less ambitious. I'm pretty sure about it. But okay, so I have to give some credit as well to Martin Jansen, who's a professor at ULB, professor of statistics, and with whom we did some of the work that I'm presenting here, and especially at the very end on sparse regression. Very quickly, let me state the problem that the kind of problems that we might want to solve. So usually, when you look at the first picture, that's an image where you see some numerical simulation results of some aeroelastic problem. So you're combining some aerodynamics, maybe with some mechanics, and so you have very complex simulation of a given physical phenomena. And so that's something you can do today. It's quite costly computationally, but you can do it. The thing is that you might want to include, or you might observe in real life, things that are on top of that. So you already have this behavior that you can model. You might want to model it even more. So more deformation on the wings, higher speeds. And so you might see even more physics appearing inside these models and inside what you observe. And you wouldn't know how to, create a model, a useful model, something that's tractable. On the second picture, what you see are some vortices. So you see the Madeira Island, and you see some vortices that are being generated by the passing of the clouds through the Madeira Island that can be seen like as a perturbation. And you could ask yourself, okay, if we use a satellite and we have those images, can we predict the speed of those vortices and how are they going to evolve? And finally, this is just an old map from Cinsano of, this is Belgium, and you see some COVID-19 cases. It can also be seen as a spatiotemporal problem. It's a very complex problem, so there is no way with what I'm going to show we can tackle that problem, but still it can be considered as a spatiotemporal problem. So you have some stuff happening in space and also varying in time. But okay, maybe in the long future, these things will be possible to be tackled. So if I try to formalize a bit better the problem itself, I would say that classically, in physics and in engineering, the mathematical models are derived from first principles, conservation laws, conservation of energy, of momentum, and sometimes you also use behavioral models. But it is not always easy, as I said, it's not always feasible or possible. And so it can be of interest to try to extract, and those are the natural laws I'm talking about. It's just about differential equations, so it's not going to be about any kind of natural law, and we could discuss about this because it's already, I'm already reducing quite a lot the problem. But okay, and I want to do this directly from observations. You will see using a machine learning perspective. So I'm going to follow the next outline. I'm going to formalize a little bit better, even better, the problem. And then I'm going to explain a very recent technique that was, well, recent neural networks that were introduced in literature, physics in for neural nets. There are other ways of doing these things. If I have some time, I might come back to those at the very end, or don't hesitate. If you have questions or other ideas, we can also discuss, because there is also state of the art on other ways of doing this. And at the very end, I'm going to try to obtain interpretable equations. So it's not just about having some regression that works well, but it's about being able to interpret the results of that regression. Because if you want to fly an aircraft using a given model, it has to be interpretable. You have to be able to explain why it does what it does, why it predicts what it predicts. It's a matter of safety and trust. So we'll see how we could do that as well. And finally, we'll jump to some conclusions. So let's specify a bit better the problem. So here on this slide, I'm already making quite some assumptions. And let's have a closer look at them. So what we ideally want to achieve is we are going to try to discover the G function that I'm showing there. So on the left-hand side of the partial of the equation of the PDE here, I'm stating that you have a field U that you derive with respect to time, and you have a right-hand side of this equation. So if I look at the bottom right here on the examples, you would see that G would look like alpha Laplacian square of U if you have the linear heat equation. Of course, this can be if you have a diffusion that is not, if you have an anisotropic material, you cannot take this out here. So you have the nonlinear heat equation, and you could, we could give other examples. Here I have the Burger's equation, which is very useful in fluid mechanics. And so what we're going to try to do is to discover the right-hand side here. How do we do this? Yeah, the idea is to try to automate this. We will have at hand some data points, so that's why it's a spatiotemporal problem. In lots of engineering problems, you have your Cartesian coordinates plus time. And what you would ideally want to have, of course, is to obtain G, but not just G, but a G function that is interpretable, something you can trust, explain, and yes. So that would be the ideal thing you want to do. Now, if I move to physics in for neural networks and how they are going to help us, as I just said before, we are trying to guess the right-hand side of the equations, which is the G function. So you can simply rewrite the partial differential equation just like that. And you're actually going to use two neural nets to try to guess G, or to have an approximation of G. So the first neural net, which is the red neural net that you have here, is basically trying to, is just fitting fitting the data that you have. And you're going to build an approximation of your field U with respect to the coordinates here. Then in green, you have, I changed the color to specify that this is, you're going to see it on many slides, automatic differentiation. For people working in machine learning, automatic differentiation is something very common, you use every day, probably. But when it comes to physics in for neural nets, people are started realizing that it's extremely useful, not just to train the neural nets, but also actually to compute partial derivatives of a very good quality. So you compute some partial derivatives of your data based on the first neural net. And actually you have to choose some terms here that you're going to input on a second neural net that is actually going to give you the right-hand side, an approximation of the right-hand side of the equation you're looking for. So there is something important here already, which is that here on the left of this neural net that is learning the PDE, you do need some prior knowledge. This is not coming out of the blue. You do need some physical knowledge. And yeah, so you need to connect these things. So this is not automatic at all. And so what the authors claim is that this is less sensitive to noise than state-of-the-art techniques. Among state-of-the-art techniques, you have symbolic regression. We can come back to that in the end if you want, and also sparse regression. But those techniques are known to be either too slow or quite sensitive to noise. Yeah, and something very important that I'm stating here is that yes, the discovered equations, are going to be casted somehow in this blue neural net, and the equation itself will be a black box here. So it might be very well fitted. It's still a black box, so you have to do something with it. You cannot just leave it like that. A major paper I'm citing here, and I can also share the slides, of course, is from Professor Reisi, 2017, and I really recommend it. Okay, so what can you do with your physics-informed neural nets? It's not just about learning the PDEs, something they've already introduced. The idea is quite old, the idea of like solving now. You can actually solve the PDE itself using the physics-informed neural nets. That idea comes back from what I read in literature to the 90s, 1998. You had a professor proposing to solve partial and ordinary differential equations using neural nets. But at that time, they had very little computing power, so the results were not very convincing. So the idea has come back today. And so now that you have discovered a given PDE, what Professor Reisi also proposes here is to actually solve it. So once you learn the equation, you keep the weights of your neural nets, of your blue neural net fixed, and you can actually choose some new initial conditions and other collocation points, and you can push it through a new neural net, which is this yellow-orange one. Of course, you have a more complex loss cost function here, but you can actually obtain interesting results here. So that's first something that I want to illustrate here. So here I'm just solving a very simple problem. So what you see here, I hope you see this is a GIF. These are GIFs that are playing. I hope you see the animation, but basically what you see here is Antarctica, which is supposed to be, it's a very unrealistic case, just for the sake of illustration. So Antarctica is supposed to be very cold. You have the sea around it, which is supposed to be hotter than the continent itself. So due to some diffusion, you actually have the water that is becoming hotter. So in this example, I'm solving the linear heat equation in 2 dimensions with some diffusion. And in this very first, here on the left, this very first GIF, I'm doing this, I'm solving the equation using a forward Euler method, so finite differences, something very, very simple. And I call that exact dynamics. And that's what I'm going to use as data. Well, at least some of these points, I'm going to use them as data to train. Let me come back here to train first a red neural net, then learn the equations from the neural net, and then push them back. Like in this case, I reused the same initial and boundary conditions, but I pushed a little bit more the time. We will see that in a second. So what I obtain from the yellow-orange is what I get here, what I call the learn dynamics. So here it's already, you do have the blue neural net I spoke about, the blue physics informal neural net that it has learned the right-hand side of the equation. And so to illustrate a little bit what training data points I'm using to do this, you have the plots below here. So here what you see, the problem is in 2D, at least in Cartesian coordinates. So you have X and Y here. And in the last dimension here, you have time. So that's why you see this three-dimensional computation domain, which is the domain in the end in which I'm solving the equation itself. And here at the very bottom, what you have, the surface there is like those are the initial conditions. So at t equals 0, you do know something about the temperature field. And then I'm also using the boundary conditions. So I'm using, you should only imagine that I'm taking the points really at the borders of the computation domain. So that's for boundary and initial conditions. So the neural nets do know those things. And then I use some collocation points inside the domain, which are chosen randomly. And you push all that through the training steps that I just described before, and you actually obtain what I'm showing here. And the result is quite nice with time, but that's for a very good reason. So here you can look at the difference. Every time that we started with the initial conditions, we can see that the match between the exact and the lower dynamics is not that good. And I'm going to come back to that in a second. But then overall with time, yeah, the difference vanishes. And it vanishes in this case for physical reasons, because we're looking at the diffusion equation. And so this thing tends to stabilize. So we wouldn't observe something as beautiful with, for example, a chaotic equation. But in this case, it works pretty well. Okay, so now moving on, I have a more complex case here where I'm solving the same problem, but in 3 dimensions. So I'm using a very cheap GPU at home. So this is already more challenging in terms of memory that you're using and also resources. And you can see already more interesting stuff. So I'm just presenting a few slices, sorry. So that's what you would see from the top. So Antarctica again is melting, and here is what you would see in a slice where you have the Z dimension. So what happens below Antarctica, and you can see that the heat is going to the bottom. So this is again using finite differences, and then I'm also first discovering the PDE and then pushing the same initial conditions, but I'm pushing the time further, which means that let me come back to my slide where I have, which means that this red neural net has never seen the times where I try to extrapolate. I'm trying to push t further than what these two have seen on this yellow-orange neural net. So when I push further is what you see here in green, what I colored here in green. And so that's what I'm calling pure extrapolation. And you see something interesting already with such a simple case. So of course, in both cases, you start with initial conditions, you see some diffusion. Again, what you can see here is that the initial conditions are poorly captured. And that's because the neural net is filtering out the little details of the coast of Antarctica, which is already a problem if, depending on what you're trying to look at. It could be a problem. If you do not really care about those details, that's okay. It's just like smoothing. But it could be problematic. Then, as I said just before, due to diffusion, this behaves very, very well. Like the mean square error between the two is decreasing. which is quite good and interesting, and hopefully it does. But of course, once we try to extrapolate, so we're pushing times that the neural nets had never seen, the mean square error is actually going up back again. And this is really problematic because it means that even though we discovered the partial differential equation, we're certainly not discovered the exact one we were looking for. So this is already showing us a limitation of these methods, even though they're interesting and certainly useful in many ways. Okay, and so one of the reasons why, that's why one of the reasons that I just showed now, that this limitation in what the neural nets, how they can extrapolate. So there's a limitation there, and we can guess they're poorly extrapolating because we know that that neural nets behave like that. But it's important, or it can be important and interesting to obtain something interpretable out of these physics-informed neural nets. So that's why I'm reusing. So this is a little bit more original. You will not find it exactly stated this way in literature, but it's based on things that are done in literature. And especially the paper from the University of Washington, the group of Nathan Kutz and Stephen Brunton. So what we do here is that we use, again, automatic differentiation to build a library of covariates. So here I have my temperature, which as I showed before was fitted on the neural net. So using AutoDiff, you can compute many partial derivatives. You can compute as many as you want. With that, you build an X matrix. Then you can also compute the partial derivative with respect to time. And you consider the linear regression problem that you see here. Now, because we know that many of these covariates are zero, or because we just chose them trying to include as many as those we think should be included there. And of course, you could include also, you can include nonlinear terms, so you can discover as well nonlinear PDEs. But because you know lots of them can be zero, it motivates the fact that we want to use some sparse regression and not just something simpler than that. So what I did here is, like, you can state the problem set up the problem as a classic lasso, and once you will obtain your beta hat, so the estimation of the coefficients that you need to use on your library, you can actually, if you multiply this by beta hat, you obtain an interpretable equation. You obtain a real PDE. You're not obtaining anymore a black box. So it's an interesting idea that is developed here. And so what I did for this problem is I tried to extract the equations on two different spots of the problem. So I'm considering again this problem of Antarctica melting, and I trained all of these networks. And I'm going to try to extract the equations out of or at least trying to extract the equations out of the red neural net, and also trying to extract the equations out of the yellow-orange neural net, using what I just showed before. So to do that, you set up this linear sparse regression problem. And I chose here 1, 2, 3, 4, 5, 6, 7 covariates. And since it's a linear heat equation, you only have 3 of them that are non-zero. So those are certainly second partial derivatives with respect to space, and all the rest are zero. So that's the ground truth, because I know how I generated the data. So I know the data generating process, I know beta. And I want to see if I can recover beta using sparse regression. So what I did here on the 2 plots on the left, I'm going to describe this. So on the very left, I'm computing the residual error. So if you look here, I'm computing the norm of y minus x times beta hat. So that's my residual error, and that's in black. And on the right-hand side, I'm plotting the prediction error. So it's x beta, so the ground truth, minus x beta hat, which is my estimation. So in a real life problem, we will never have access to the prediction error because we do not know the ground truth. But since I do know the ground truth, I'm using these to verify if I'm recovering properly the equations. So that's what you see here in red. You see the prediction error. And here in black, you see many curves out of the residual error. And that's because I'm using a cross validation here. So I used 200 folds. So you see 200 of those lines to try to have something a bit more robust. What you see here is that when you try to extract, well, what you would expect actually in any case is that your, at least your prediction error should behave as well as your, well, you would love that the minimum of your prediction error coincides with a residual error, and that they behave identically. This is clearly not the case. So what we can conclude here is that it's not possible to actually extract the equations from this red neural net. And the very simple reason is that even if you fit very well these neural nets on the data, so on temperature points, in between points, the derivatives are not trained. So you have good quality of temperatures, but trends across points are totally wrong. So something a bit smarter to do is to use physics informed neural nets till the end. Use the blue neural net, then train this orange one, and you try actually to extract the equations from here. And then you're going to try something that behaves much more beautifully. So that's what you see here on the plots. So again, you have the residual error on the left, the prediction error on the right. And so here the minima of both is quite flat. So I cannot claim you can distinguish a lot what happens here, but that's why I plotted 3 different solutions just to each other, just to see how sensitive it is. And what you see here is that you're getting close to the ground truth. So if I look at the first vector of beta hat, I did have a 0 for the first term, a 0 for the second, something close to 2, and then something close to 0, something close to 2, something close to 0, and something close to 2. So I'm not getting, I don't have exactly the ground truth, but I'm getting there. And yeah, I prototyped this for illustrational purposes. I didn't push it to the point of trying to go further. I'm just showing that it's a good idea to do it, to try to extract the equations after using some physics informed neural nets. Okay, now let me recap a little bit with some conclusion and speak about some future work. So what I have tried to do here and to show you is how to discover PDEs from spatiotemporal data. Physics informed neural nets are supposed to be less noise sensitive than what you would find in state-of-the-art like symbolic regression, sparse regression. And we have combined it with sparse regression to obtain interpretable equations. And with the help of something that is quite obvious for the machine learning community, automatic differentiation, but is probably less obvious for an engineering community, which is non-computer scientists, I would say. So the results are actually encouraging what I showed you, but there are of course some limitations. So there is nothing in literature that helps to tackle the number of parameters that you choose inside your Bruno neural net. So you have your Bruno neural net, your physics informal neural net here. Obviously, when you do not know the equation, you're going to put here more terms than the ones you need, obviously. And so, yeah, you should address somehow the fact that this might be overfitting. So this is not addressed in literature. So certainly something needs to be done there. Of course, I'm using sparse regression after using a physics informal neural net, and so I'm limiting what I can do, because sparse regression you're already imposing a lot of structure in your equation, so you can discover less things. Whereas the physics informal neural nets are just connecting the inputs, so they can go very crazy in the regression problem. So it's that's a limitation of what I showed. And finally, what I would say is that both methods require some physical knowledge, prior physical knowledge. So it's not that automatic, but of course we would expect that, I guess. Finally, some future work. Of course, I showed some Antarctica dynamics, if we can call them like that. They were too simplistic, so that's not really useful. If we want to tackle challenging and interesting problems, we should be looking at multi-physical problems where you will have multiple timescales and see how well these things behave. Another very interesting problem we might be looking into in the future is that in real life, usually when you do experiments, you might change a little bit the initial conditions and the boundary conditions, because that's how experiments are done, and you might not be able to always use those same initial and boundary conditions. So the question is, can we still extract the equations if we do know that across several experiments, the underlying governing equations should be similar, but you might have some variations in the parameters of those equations. A little bit connected to that is, what about long-term predictions? So if we talk about a chaotic system, which is known to be sensitive to initial conditions, it's usually very hard to do long-term predictions. So the short-term answer to this, does it work with a chaotic system? The short answer is no, and we have already why, but so that there are things that need to be done there to improve that. And finally, another problem, which is a major one, and also I think very interesting for applications, is that usually in real life, you cannot measure everything you want. So I just showed this problem of Antarctica, and I was actually using the third dimension of the temperature field. But if you would use a satellite to get infrared images of Antarctica melting, you wouldn't be able to use the third dimension in Z. So that's quite problematic. Can we tackle the problem somehow? Well, our first idea, and we might also look at that in the future, is how we could impose some extra physical properties. So if you know, you don't see what happens in the third dimension, but you do know that up to some point, up to some depth, your domain is isotropic, then you might be able to do something there. And so could we embed some invariances? So the invariance of diffusion property across space, that's also an interesting question that we might look at in the future. And finally, something else is that so I'm going to join a group who's already working on some of these topics. And we are developing, and it's already developed, some of it is already developed, especially using sparse regression on how to actually obtain the underlying PDEs using a Python library that is already quite well written by our group. So our group is a group of CRI research, which is Centre de Recherche Interdisciplinaire at University of Paris. And yes, we're going to push into this direction, write some software, and hopefully also write some papers to share with all of you. Thank you very much for your attention. And if you have some questions, please do not hesitate.
Thanks a lot. It was very interesting. So times for questions. So I'll leave the floor to the audience. So don't be shy. If you have any questions, just unmute your micro and ask.
Yes, thank you very much for the presentation. It was really interesting. My question is more of application of your work, because so you would find those underlying equations. Would it be to afterwards to be in a complement with experimental data and or modelization and simulation study of those kind of things? And a second question would be, did you also try to, so because you're talking about here Antarctica and these kind of things, but so I'm a bioinformatician, so I was curious, did you also try to maybe study biological phenomenon, because there is a lot of physics also there, so it's yeah.
Okay. Yes, so for the first question about how there are many ways in which we could use this physics-informed neural net. So indeed, you could combine experimental data plus models in many ways. So if you have some of the partial differential equation that you know, it behaves like that. So you do have the behavior, and you have data for some part of the differential equation, and you're looking for another field, then you could use this method. Like the first thing, I think the first application which is very useful is, for example, when you're observing in fluid dynamics, you're observing some flow, and you do have the velocities of the flow that you were able to capture somehow, and you want to infer on the pressures, the underlying pressures. So that's something I've seen in literature that has been used. So there are many ways in which you could combine data and models, not just discovering the models, and then you could also just discover the models and then simulate based on the results. But of course, that's not the only application. Yes, application ways. Actually, we're looking into something in biophysics. So at CRI Research, there are lots of people working in biophysics, and so we're going to try to understand how birds produce sound. So it's about aeroacoustics and mechanics. And the idea behind is to say that so birds produce sound in a more it's not really a beautiful way, but like the idea would be to mimic some of the mechanisms that the birds use to produce sound, to build a prosthesis for humans, which have lots of limitations. So definitely, we're not going to look just at the problems I'm presenting here, but certainly lots of applications.
Thank you very much. I love the bird talking story. I will look into it. Thanks.
Welcome.
Thank you. So there is Jacopo who wants to ask something. Please, Jacopo.
Yeah, thank you, George, for the very interesting presentation. I have a couple of questions. The first one is about the physics-induced neural network. The architecture you showed into your slides seems to be, to me, like multi-layer perceptron feed-forward one. I was wondering, is this the case? Is this the architecture that is used, or maybe other neural network like a recurrent neural network or convolutional one are also used?
So as it was first introduced, it is just a simple feed-forward MLP. So here for the purpose of drawing, I chose the same architecture, but obviously you're not going to choose the same complexity for both. It's a bit more complex to fit the data than what you need for the regression problem of the equations. So that's how it was initially introduced. Now in the Python library that we are developing, you can choose, there is no reason why you should just use a DNN to approximate the equation. So we are allowing, you would be free on choosing what you want to, how you want to regress the data, and how you want to regress the equations. So it's a modular thing where you can do as you want.
Nice. I will definitely have a look to the library. So, and my second question was like, so I saw that you introduced in the second part of your work, the second regression problem as like a separate problem on, let's say, the output of the neural network. I was wondering, in the literature, has it been used or have you considered introducing a similar kind of constraint, but directly into the neural network by means of a loss function, custom loss function, trying to account for like the physical properties for example, you were mentioning, or is it too complex, too difficult to interpret?
I've seen things that go in that direction. Like the team that develops deep mode, they propose something that goes in that direction. So they're not splitting into the problem, at the very beginning at least. Now, if you want to make it modular, and that's what we're aiming for in the future, we need to separate the problem. But at the very beginning, they did something totally integrated. So there was no separation between the red and the orange neural net. So you directly go to try to train the last one. And in the middle, you use my loss function plus the data. So you could directly go to for example, doing predictions. Definitely you can imagine architectures that are doing this in a single problem. Now, why don't we do it now? Why don't we do it now? Maybe because, I would say there are different purposes. Like for me, the first purpose, I would try to get the equations right. Like, can we, I have no clear answer on why we are not doing this already. But I think there are ideas around that. Yes, it's a good idea.
Well, that opened up for more research topic, but it was interesting to understand. So it's mostly, you would say, our interpretability choice for you to separate or to integrate the.
Yes, for me in the first place, it was also to understand exactly, to show why it's interesting to use that blue neural net, because if a bit naively, I asked myself, okay, why don't I extract directly the equations from the red one? Well, that doesn't really work.
Okay, thank you very much.
Okay, thank you. So I had some more questions. I wanted to challenge a little bit the rationale of your approach. So the differential equation, partial differential equation, which are continuous time, are not always the easiest thing to write down to model something. And then once you want to use it, you need to integrate them, and then you need to go back to the discrete numeric domain. So apparently you start from a discrete time numeric data to go back to a continuous time domain to go back at the end. So I was wondering a little bit if this makes sense. And then the other things is how many samples at the end of the day you are using for doing that, because I have the feeling that you're producing your data from simulation, so you have a huge amount of data. How much is realistic in
Yeah, indeed. I'm if I go, I think I have something more here. Yes, here I'm showing exactly how I'm solving. Here there's a minus problem, but I am using discrete data. But once you solve it, you can stay with your neural nets. So you can stay all the way discrete. But yes, that's quite a good question. And here I'm showing amounts. So this is for, yeah, this is for the 2D problem. So you're quite limited. So I do need some boundary and initial conditions. So in a real life problem, you cannot choose them. I haven't tried reducing those, but I mean, you cannot play with a number there. Well, you have what you get, but yeah, here I'm saying that you have also collocation points and it's coming for free. It's not really true because you need some temperature. No, yes, sorry, this is for solving. This is not for, this is not to discover the PD. This is just to solve. So when you're solving the equation, the collocation points come from free. So you don't need, so those are coordinates that you choose. So if you want to solve it, then it's for free. But actually, if you want to do the discovery, yeah, it's very slow. It's I cannot. This is also for the
some noisy data.
Sorry, I haven't tried on my side with noisy data, but there are results in literature where they use noisy data, and it works quite well. But yes, indeed, it is extremely slow. Like if you compare the time it takes me to solve the equation using finite differences and my neural nets, yeah, you're 100 or more or 1,000 times slower. So it's probably a bad idea to try to solve these equations using neural nets. Yeah, I cannot claim it's fast. Yeah.
I had the last questions about the assessment. So you use an assessment based on quadratic error, while at the end of the day, you have a dynamical system. So probably you should care also for property of stabilities. You mentioned the chaotic systems, but in general, I mean, if you fit something which does not respect the real dynamic, most important properties, which are not only numeric, it's more about stability or, attractors, or I mean, more qualitative properties. Would it make sense to introduce them in?
Of course, it would be great if we could stability, for example. Yeah, it would be great. Something we were also, thinking that would be very interesting to be able to impose is like energy conservation. If we're looking into physics, how do we make sure that these things are energy conserving? We don't know how to do that.
Because I've seen some research on people trying to fit to this, to learn a Lyapunov function for stabilizing systems. So I guess that, I mean, you could integrate them in.
If we can, if we can. They're trying to discover the Lyapunov function, right? Or they do know it?
I've seen something like that, but I mean, I guess that there is indeed some direction, some dynamic property that you could try to force in your solution.
That would be great. If, for example, if by transforming a little bit how this problem is set up and you're able to discover Lyapunov functions, it has a huge added value, I would say. Now, what I like here is that we're not imposing, we're trying to discover the equations. So even if I'm looking at the quadratic errors, I'm doing this at the level of the equation, not exactly at the level of the time series itself.
Mm-hmm.
So that's a bit, it's a little bit higher level, which it's also interesting, I would say.
Okay. So unless there are other questions, I wish to thank you again. So I would like just to invite also the community, the people attending. So since we are slightly moving to a period of a second lockdown, I think it's important to keep the community active. So if you have ideas for presentation, if you want to present, I mean, you can organize yourself, but I think it's important that even in a virtual manner, seminars keep on going on. And I realize there's been a long shutdown period also in terms of also online seminars. So I think it's a bad idea in general. So if we, as MLG, can give help, don't hesitate to contact us, or if you have people to invite, or if you want to present. That's all, I guess. So in terms of participants, I mean, we had around 30 participants, which is larger than the average we have at our seminar. So I think it's good news. So it means that people can keep on working, or at least attending interesting presentation like today, even in our bad conditions. So thanks again. And so,
thank you very much.
Can you send me the transparency, the slides, so in case I forward to people? And I think we'll make this presentation available on our YouTube channel because there are other professors asking for that, if it's good for you.
Sure, sure.
Okay, so take care.
Thank you very much. Thank you for attending.
Bye-bye, yeah. Have a nice day.
Bye.
Bye.